History of Vector Analysis, Episode 4, Algebraic Properties of Complex Numbers. You are here. Hey, it's old Doc Goler. Welcome back. In the last episode, we talked about how Leonhard Euler came to express what we today call complex numbers in the form of a single mathematical object, often represented by the letter Z. The concept of single mathematical object is the key there. Mathematicians did not really know what these imaginary or complex numbers were, but by the 1780s they were pretty clear on how they behaved. In this episode, I'm not going to discuss much in the way of history. Rather, I will describe the properties of complex numbers as mathematical objects, as they were understood at the time of Euler's death in 1783, which is essentially the same way we understand them algebraically today. I ask you to bear with me on this. I need to lay out this 6th to 10th grade stuff explicitly so that I can compare and contrast it later with quaternions and especially modern vectors, which behave very differently. As you troubled physics majors have probably learned the hard way already, math and science courses have a way of going from the trivial to the incomprehensible in the turn of a page. So don't be lulled into a false sense of security with this stuff, okay? It gets weird in a hurry. The rules of arithmetic for real numbers were well established by this time, and many of them, 2 plus 3 equals 3 plus 2, date back to prehistory. Some of the rules for adding and subtracting complex numbers were developed as soon as they were invented/discovered. Cardano argued that plus z minus z equals 0 in 1545. But what about multiplication and division, exponentiation? It was Euler's definition of complex numbers, z equals a plus ib, that allowed us to formalize the modern rules for complex arithmetic. We begin by defining three complex numbers, z1, z2, and z3, all in the form of a plus ib. Euler himself, in the same work where he defined z in this way, showed that the rules for adding z1 and z2 are the ones that we know today. You add the real and imaginary parts separately using the properties of real numbers that have already been established, and then you recombine. The statement is not as trivial as it may seem. Implied within it are that real and imaginary numbers are truly independent of each other, kind of orthogonal, if you will. From this rule or proposition, it is straightforward to show that z1 plus z2 equals z2 plus z1, proof that complex numbers are commutative under the operation of addition. It is similarly straightforward to prove that the associative property of complex numbers under addition. All right, that's 2 down. Up next, is there an identity property for complex addition? That is, in the set of complex numbers, is there a number z sub ai for additive identity, such that any number z plus zai equals z itself? And the answer is, sure, of course. Okay, it's 0. Thus, complex numbers possess an identity property for addition. The next step is to show that complex numbers also have an inverse property for addition. This time the question is, for every number z in the set of complex numbers, is there another z, let's call it minus z instead of z to the minus 1, but we could go either way, such that z plus minus z equals zai, the identity? The answer again is, of course, you simply multiply z by negative 1 to get minus z. This works for negative numbers as well as for positive ones. Thus, complex numbers have an inverse property for addition. This is always important because you need this property to define the operation of subtraction. That is, because complex numbers have an inverse property for addition, we can conclude that subtraction is defined for complex numbers. It is identical to adding negative 1 times the number to be subtracted. Let's move on to multiplication. Back in Ars Magna, Cardano used the Arabic technique of cross-multiplying quantity a plus b times quantity c plus d to get the following result, which turned out well. From this, he showed that the complex roots he got via the quadratic formula led to the associated quadratic equation summing to 0. There is a tacit assumption here that real numbers and imaginary numbers commute. This was not really a proof, it was more just a guess, but Euler, using his definition of z equals a plus ib, does succeed in proving it. And hey, it's good enough for Euler. Okay, so with Euler's blessing, we can go ahead and use the properties of real numbers to manipulate the product to show that z1 times z2 equals z2 times z1. Complex numbers are commutative under multiplication. Spoiler alert. This is going to be the first place where quaternions and later vectors will deviate from normal. Neither of them commute. Next, are complex numbers associative under multiplication? That is, we have the question, is z1 times the quantity z2 times z3 equal to the quantity z1 times z2 times z3? First, we'll evaluate the left side, then the right side, and then we'll compare terms. Okay, this is where things really get tedious. z2 times z3 yields 4 terms, 2 real and 2 imaginary. Here they are. z1 times the product of z2 times z3 yields 8 terms. Again, here they are, grouped into 4 reals and 4 imaginaries. We repeat this process for the other side and end up with this expression. So, are these two expressions equal, the yellow and the green boxes? The next step is to compare terms. By the way, all of these charts are available on the website if you want to go through them. Here are the 2 equations copied from the previous slide. I will save you the headache and show you that in fact, for each term in the upper expression, there is a corresponding one in the lower expression, including the correct sign. Note that the comparison job is simplified to a degree by the fact that we must have the real terms match up to other real terms and the imaginary terms match up to other imaginary terms, hence the color coding of the lines. So once again, we have victory. Complex numbers are associative under multiplication. In order to save a minute or two of time, and because we'll learn nothing new from it, I will simply state without proof that complex numbers also satisfy the distributive property of multiplication over addition. We're not done yet. We still need to investigate the identity and inverse properties for multiplication because we need the latter to define complex division. Again, we ask the fundamental question, in the set of complex numbers, is there a number z sub mi for multiplicative identity this time, such that z times zmi equals z for all z? Well, sure. The answer is z sub mi equals 1, where we should explicitly state that by 1 we mean z equals a plus ib, where a equals 1 and b equals 0. We can prove this by multiplying out the terms, so we can conclude that complex numbers possess an identity property for multiplication. Time for the inverse. This time the question is, for every z in the set of complex numbers, is there also an inverse of z, let's call it z to the minus 1, such that z times z to the minus 1 equals z sub mi, the multiplicative identity? This one's a bit trickier. It's not obvious to the uninitiated what you have to multiply the quantity a plus ib by in order to get 1. The default way to approach problems like this is to assume that the multiplicative inverse of z is the reciprocal of z, like it is in real numbers, z over z equals 1 and all that. If we get consistency later on rather than divide by 0 chaos, then we're on solid ground. Okay, if z equals a plus ib, then 1 over z can be expressed like this. Is this okay? Are we even allowed to have imaginary numbers in the denominator? The standard approach at this point is to use algebra to get I out of the denominator if possible. We can do this by the now standard trick. We note that if you multiply a plus ib by the quantity a minus ib, that the cross terms in the imaginary part cancel out, leaving us with a pure real number. This trick is so powerful and so widely used that we have given a minus ib its own name, the complex conjugate of z, often expressed as z star. Let's apply this trick. We start with our definition of 1 over z, and then we multiply it by 1 in the form of a minus ib over itself. The numerator is a minus ib. The denominator, thanks to our trick, is a squared plus b squared, which is a real number. Thus, we have successfully removed I from the denominator. What we have left is this. where k is a real constant defined as 1 over a squared plus b squared. The key thing to notice here is that the product is of the form a plus ib. The minus sign here means nothing since all positive and negative numbers are in the set of complex numbers, so it just doesn't matter. Well, this is really encouraging. It implies that division is defined for complex numbers. Still, we should check. Let's multiply z plus 1 over z and make sure that we get unity. Well, happily we do. We get the quantity a squared over b squared, a real number, over itself, and we have established long ago that any real number divided by itself is unity. Hence, any complex number divided by itself is also unity, as is any imaginary number divided by itself. That is, I divided by I equals 1. All of this, for the record, means not only this, but it also means that complex numbers possess an inverse property for multiplication, and division is defined for complex numbers. So that I in the denominator earlier on turns out to be okay after all. Still, it is common practice to use complex conjugate approach to express final results in the form where I appears only in the numerator or in the numerator of an exponent. Let's take a step back and gaze upon the wondrous monstrosity that are complex numbers. The fact is that based on their properties, they are remarkably well behaved. In fact, they are better behaved than real numbers. If you take the square root of a real negative number, you get kicked out of the set of real numbers. Not so with complex numbers. If you take the square root of any complex number, positive, negative, or in between, the result is another complex number. The only way I know to get kicked out of the set of complex numbers is to divide by 0. Okay, that landmine is still there. So, algebraically, the set of complex numbers are great. They're fabulous. They're the best we've ever had. Geometrically, however, as of Euler's time, they remained impossible. This is not lost on Euler, who in his heart seems to be a geometer despite his algebraic brilliance. Nonetheless, by 1800 it was clear complex numbers can be treated as legitimate algebraic objects, and whether you like them or not, the power of algebra renders them legitimate mathematical objects. Okay, I reiterate, I'm making a big deal out of this well-behaved nature of complex numbers because later I'm going to show that quaternions, and then especially vectors, are not nearly so well behaved. Let's summarize what we know, or at least what we've agreed upon regarding the multiplication of imaginary numbers and real numbers. All right, we established long ago that 1 times 1 equals 1. Thanks to Brahmagupta and the Crusades, we know that 1 times -1 equals -1, and -1 times -1 equals +1. This last one in particular is non-trivial, and even Euler struggled with it, but that's another story for another time. Now, thanks to folks from Cardano to Euler, we have established that I times I equals -1, I times 0 equals 0, and I times 1 equals I. All right, what else have we got? All right, well, what is -1 times I? It appears that we have demonstrated that -1 times I equals -I. This is another of those subtle but important points. A number, that is a mathematical object, can be both negative and imaginary at the same time. It's not a one or the other kind of a thing, two distinct adjectives, if you will. We can summarize this in what might be called a complex multiplication table. Since there are 4 values whose magnitude is 1, and they are either pure real or pure imaginary, positive and -1, and separately positive and -I, we end up with 16 terms in our table. So that's it for this episode. In the next episode, we'll get back to history. I will show you how a Norwegian named Caspar Wessel identified an interesting pattern in that multiplication table, one that finally yielded a sort of geometric interpretation of complex numbers. I say sort of because it requires you to suspend a certain amount of disbelief with regard to what came to be known as the complex plane. All right, see you then.